Today's cars operate as mobile data centers, propelled by millions of lines of code. With fly-by-wire controls, steering and braking depend entirely on digital logic. To manage the risk of a system crash, the automotive industry relies on a rigorous international framework known as ISO26262. It dictates exactly how engineers must identify hazards, assess risk, and assign strict safety integrity levels to every critical component. Fault tree analysis, or FTA, serves as the primary deductive verification method required by ISO 26262. It forces engineers to define a catastrophic top-level event and systematically trace every logical pathway that could cause it. This method has a strict pedigree. In 1962, Bell Labs created FTA to secure the launch control systems of the Minuteman nuclear missile. The mathematical rigor required to prevent an accidental launch set the baseline for modern systems engineering. The methodology proved so reliable, it moved into commercial aviation validation, securing the Boeing 747 before becoming a mandated tool for mass-market automotive networks. Today, ISO 26262 requires engineers to use FTA to prove an ultra-strict quantitative target called the probabilistic metric for hardware failure. For the highest risk category, ASLD, the system must demonstrate fewer than 10 failures in a billion operating hours. But applying a mid-century aerospace tool to the highly integrated networks of a modern car creates an unseen mathematical paradox. The strict quantitative logic that worked for isolated mechanical systems breaks down when applied to millions of interdependent components. This diagram shows a standard fault tree for an electronic parking brake. We start at the red node at the top event, and map the logic backward. At the component level, analysts classify root causes into 3 categories: primary, secondary, and command. Primary faults are intrinsic hardware failures. This is a component breaking down due to internal wear, fatigue, or aging while operating within its designed limits. Command faults occur when the hardware is functioning perfectly, but it receives a corrupted signal or an incorrect software instruction from an upstream source. Secondary faults are failures triggered by the environment. These include stresses caused by extreme temperature spikes, mechanical vibration, or severe electromagnetic interference. A common industry practice is to map all 3 of these fault types into a single, massive fault tree. Engineers assign a probability to the physical wear, the command logic, and the environmental stress, wiring them all into the same probability equation. Treating environmental stress exactly like physical wear and software logic inside a rigid equation is a statistical error. It generates false data that actively compromises the safety validation of the entire vehicle. This structure illustrates a fault tree and gate connecting 2 redundant microcontrollers. To calculate the total failure probability here, the math relies on a strict foundational law. The input events must be statistically independent. If microcontroller A fails because of microscopic internal wear, it has no bearing on the likelihood of microcontroller B failing. The equation remains valid. But secondary faults operate differently. A severe environmental stress, like a massive voltage spike from a shared power converter, hits the entire system at once. The spike degrades multiple components simultaneously, instantly breaking the independent probability equation. The failure of Unit B is now directly conditional on the external factor that destroyed Unit A. To accurately calculate these dependent states, analysts would have to abandon simple Boolean math and use Markov chain analysis. Applying that level of modeling to a modern billion-transistor system requires processing power and timelines that far exceed practical engineering schedules. Attempting to force variables like temperature and power fluctuations onto every component branch causes a state explosion. The fault tree multiplies until the diagram becomes a dense, unreadable forest of data. Forcing secondary faults into a quantitative matrix destroys the tool's utility. It generates a mathematically invalid hardware metric and hides the actual architectural weaknesses engineers need to fix. To resolve this mathematical trap, leading automotive suppliers use a structural strategy known as divide and conquer. They take a necessary step. Analysts completely strip all secondary fault branches and environmental variables out of the quantitative fault tree. What remains is a pure PCAS fault tree. It is a streamlined logic model containing only independent physical hardware failures and clear logical signal paths. With the dependency variables removed, the probability calculation resolves accurately. The secondary faults are not ignored. They are relocated to a separate qualitative architectural domain known as Dependent Failure Analysis, or DFA. DFA acts as an architectural firewall. Its purpose is to systematically identify and physically block common cause failures and cascading failures before they can spread. Engineers use a rigid checklist of 7 coupling factors to hunt down vulnerabilities, thoroughly evaluating shared resources, communication paths, and identical component types. In practice, analysts inject digital errors into a shared memory block to see if the corruption spreads. If it does, they implement memory protection units to quarantine the bad data behind a digital barrier. By moving secondary faults into the DFA process, engineers shift the burden of environmental chaos off of a fragile mathematical equation and onto a robust system of physical and architectural defenses. For the pure PTC fault tree to calculate a valid hardware failure metric, every parallel element in the equation must remain mathematically independent. Simply drawing 2 microcontrollers on separate branches of a diagram does not grant them physical isolation. The hardware still shares the same circuit board, the same power supply, and the same ambient heat. The DFA serves as the legalizer for the fault tree, proving the independence assumption is true in the physical hardware. The DFA report formally proves freedom from interference. By documenting physical boundaries like galvanic isolation and memory partitioning, it legitimizes the Boolean math. The PTC fault tree delivers the uncompromising quantitative probability, while the dependent failure analysis provides the necessary structural reality. A fault tree without DFA is a mathematical fiction. A DFA without a fault tree is qualitative guesswork without verifiable proof. This synergy is the basis for ASIL decomposition, an architectural strategy used to execute complex tasks like autonomous steering without pushing development costs to impossible levels. Decomposition splits a single extreme ASIL-D safety requirement into 2 separate parallel pathways rated at the lower ASIL-B level. The PC fault tree calculates that the combined probability of both pathways failing meets the target of under 10 failures per billion hours. Simultaneously, the DFA proves these pathways use separate power and diverse algorithms, ensuring no single event destroys both. This verification is critical as vehicles shift toward highly integrated system-on-chips, where resources are hyper-shared and true isolation is harder to achieve than ever. Mastering the synergy between quantitative fault trees and qualitative architectural defense is the only way to build resilient systems, even when the environment fails. It is the definitive method to guarantee fault tolerance in vehicles that must protect human lives without a driver's intervention.